Hello everyone from Math 2000, Linear Algebra. It's Professor Wenson here again with a video on your section 7.6 from Zybooks titled Change of Bases and Matrices of Linear Transformations. And there's going to be a lot of new notation in this section. Now you've seen a change of basis matrix before, a transition between coordinate matrices in a previous section. This will tie into that. This is similar, but maybe a little more involved, as you'll see. And I'm hoping when I go through several examples, and maybe watching this video and some of the other ones I've put up, hoping seeing all this stuff will help you understand what's going on. All right. So a linear transformation is normally expressed with respect to the standard basis for the domain and codomain. Right. Usually when you see a rule for a transformation, the input and output are just coordinates, really, relative to the standard basis for the domain and codomain. That's what that's saying. However, a procedure exists to find a matrix representation for a transformation that maps elements with respect to non-standard bases for both the domain and the codomain. So you got first part of this section is on writing the matrix representation of a linear transformation with respect to non-standard bases. All right. So the standard matrix of a linear transformation from U to V is a mapping between coordinates with respect to standard bases. Right now, again, this is what you're used to. Right? All the stuff involving the standard matrix, a mapping between coordinates in relative to the standard bases of the domain and codomain. That's what you're used to so far. But more generally, suppose we have a basis for the domain called B and a basis for the codomain called C. Right? Suppose these are non-standard ordered bases, and they say ordered because the order that you write the vectors in will matter. Well, then you can find coordinates. You can plug in. What all this stuff is saying here is that you can plug in the basis vectors from the domain, and then take their output, take the images, and find the coordinates relative to the basis C for the codomain. So that's all this stuff is saying here. And then those coordinate vectors will make up the columns of what's called the matrix representation of the transformation with respect to those non-standard bases B and C. And here's the notation for it. You got little braces around the name of the transformation. The basis for the domain on the lower right, the basis for the codomain in the upper right. Again, all this part is saying is that these coordinate vectors for the images make up the columns of our matrix representation. All right. And then this here, I'll get to, I'll show you some examples. This is a lot of notation. This is saying that the coordinates of an output, the coordinates of an output relative to a basis for the codomain is equivalent to this matrix representation multiplied by the coordinates of the input relative to the basis for the domain. All right, again, I'll show you examples of this. Hopefully you'll understand more of what this is saying, more of what this means when I actually get to an example. And they go through a procedure here. I'm just going to develop this procedure with my first example. You can read that on your own if you want. All right, so we're given an example of a transformation here, which I'll go to a piece of paper and write out. So here is the transformation that we're given. Now I'll get to those non-standard bases in a second. But for right now, I want to just refresh your memory as to what we're used to. All right, we're used to working with the standard bases. Right. Now the standard basis for R2 I'll just call, I'll call for the domain R2, I'll call that little E1. And this is the vectors, 1, 0, and 0, 1. Right, like that. And this is also the standard basis for R2, which I'll call E2 as well. All right, so E1, standard basis for the domain. E2, standard basis for the codomain. They're both the same set. So it's the same set of vectors, 1, 0, 0, 1. So when you're given a transformation, again, what we're used to, the input, this vector with components x1 and x2, you can think of these as just the coordinates relative to E1. Right, the coordinates relative to the standard basis. And the same thing for the outputs. Right? When again, what you're used to is when I'm given a transformation, a rule for it. These components of the output, you could think of these as coordinates relative to E2, the standard basis for the codomain. I'll just say coordinates relative to E2. For example, if I just, I'll plug in an input from R2 and then get an output. So if I said, what's T of, the vector, say 5, 4? Well, if I run this through this rule, this would be a 9, 1. 9, 1. Now like I said, my input, 5, 4. Right? You can think of this 5 and this 4 as coordinates relative to 1, 0, 0, 1. Because I can write this vector as 5 times that first basis vector, 1, 0, plus 4 times the second basis vector, 0, 1. Right? So again, you can think of your input as coordinates relative to the standard basis. Same thing for the output. Right? This 9, 1. And you can think of the output here as coordinates relative to the standard basis. Right? This vector is 9 of that first standard basis vector, 9 times 1, 0, plus 1 of the second basis vector, 0, 1. Okay, so again, this is what you're used to. This is what we're used to. Going from standard basis vectors to standard basis coordinates to standard basis coordinates. But now we're going to do something totally different. Now, instead of going from, instead of my input being in standard basis coordinates and my output being in standard basis coordinates, we're going to change it up. So now we have this B that's given to us, this set B with the vectors 1, 2 and the vector 3, 4. This is a basis for the domain R2, right? A non-standard basis. Right? And then this C, right? Let's maybe scratch this stuff out, these bars, these lines. C, this other set they're given to us, with the vectors 1, 4 and 2, 3 in it. This is another basis for R2, but we're going to, it's a basis for the codomain R2. Right? This is a basis for the codomain R2. So now what I want to find is this. Now what I want to do is this. we would like, or we want the following. I want to go T of, and then plug in coordinates. I want to set up a new rule where my input will be coordinates relative to basis B, relative to the domain basis, and have the output be some matrix. Right, and this matrix was denoted this way. This is a matrix. This is the matrix representation of T relative to B and C multiplied by, again, those coordinates relative to B. And this output should be the the coordinates of this thing relative to C. Right. So when I multiply these two, they end up giving me coordinates relative to C, the basis for the codomain, relative to C. All right. So how do we find this matrix? So first I'm going to find this matrix that they're asking us for here. So again, this is called the matrix representation of T with respect to or relative to basis B for the domain and basis C for the codomain. Again, the notation for this is this, bracket around the name of the transformation. Basis for the basis for the domain in the lower right, basis for the codomain in the upper right. And when these are both the standard basis, this is just the standard matrix. Right? If B and C are the standard bases, then this matrix is the standard matrix. All right. So how do we do this? Well, just like you found the standard matrix. All right, just like you found the standard matrix. So number one, we plug in. I take the basis vectors for the domain and I plug those into my rule. I find their images. Plug in vectors from the domain basis. All right, so what is T of this vector 1, 2? If I apply this rule to the vector 1, 2, I'd get the output 3, negative 1. 1 plus 2, 1 minus 2. Alright, that's when I plug in the first basis vector from B there, and then plug in the second one, plug in 3, 4. And I'd get, 7, negative 1. 3 plus 4, 3 minus 4. Alright. Now, normally, right, remember back when we were working on finding the standard matrix, remember these would be like the columns of the standard matrix, but that's not the case here. We're not working with the standard basis for the codomain. We want to find the coordinates relative to this basis, basis C for the codomain. So now I'm going to find the coordinates of these images, right? 3, negative 1 and 7, negative 1. Relative to C, right? Relative to that basis, that ordered basis for the codomain. So that means we want to solve the following. I want to find, what are some constants C1 and C2 such that, C1 times the first base vector from C plus C2 times the second vector from C. I want to know what are these coordinates, what are these numbers, so that this linear combination gives me this image, right? The output of the first basis vector from B. So I want this to be equal to 3, -1. But at the same time, also, I would like to find, some coordinates of this vector. What are the coordinates of 7, -1 relative to basis C? So I say C3 times 1, 4 plus C4 times 2, 3 equal to, 7, -1. And you solve these separately, but what I'm going to do is kind of go and put these together. Like, remember if you were solving a system like the top one here, you'd set up a little augmented matrix where down the first column, you have the coefficients of C1, the first coordinate, and then the coefficients of C2, then a bar, and then what you want them to be equal to, 3, -1, like that, right? And if I were doing the same thing here, I'd set up an augmented matrix where, coefficients of the first coordinate down the first column, coefficients of the second coordinate down the second column, and then what I want them to be equal to, right, this 7, -1. Well, do you notice how both of these have the same coefficient matrix, right? So we can really do these at the same time in one big augmented matrix. Right, so I'm going to put these together down here. So where we have this same coefficient matrix on the left, 1, 4, 2, 3 bar, and then 3, -1 was one of the vectors I wanted to find the coordinates of, and then 7, -1 was the other vector I wanted to find the coordinates of. And I can kind of combine these, put them together as one big augmented matrix. All right, so what you're seeing over here are the vectors from C, and what you're seeing over here are the images of the vectors from B. All right, and that's exactly what they were telling us to do here. All right, so back in this procedure area, how do I find this matrix representation? See, the C is the vectors V1 through Vm. See, they're putting those on the left of the bar. And then, B is the basis vectors for the domain. That's U1 through UN. You see they're doing T of those. They're putting their images on the right side. And then put this into reduced row echelon form, and then you'll have your matrix representation. All right. So back to my page here. So yeah, so I'm going to put this, I'll go to a calculator, or you could, there's only 2 rows here. It probably wouldn't take that long to put this into reduced row echelon form. Right. Yeah, so I'll just go to a calculator here, and hopefully remember how to enter matrices. Right. Second matrix, edit. This augmented matrix I made here is a 2 by 4, 2 by 4, and then you have first row, and I'm going to come back when it's all done and I put it in reduced echelon form. Okay, so I've done that, and let me write it here. You got 1, 0, 0, 1, and then -2.2. Now if you want to change it to fractions, that'd be fine too, right? This would be a -22 tenths or -11 fifths, right? And -4.6, 2.6, and 5.8. If you want to change them to fractions, that's cool too. But remember what these are giving me. These are giving me coordinates. It's telling me that this vector 3, -1, I'd need -2.2 of the first vector from C and 2.6 of the second vector from C. Right, if I let me show you. Right, so 3, -1, right? That 3, -1 we had. If I take -2.2 times the first vector from C, right, times 1, 4, plus 2.6 times the second vector from C, that was the 2, 3. This should be true. All right, and look at this. Negative 2.2 plus 5.2 is 3. Negative 8.8 plus 7.8 is negative 1. Right? So this works. And then, we were writing this second column is the coordinates of the vector 7, negative 1 relative to C as well. That vector 7, negative 1 is, negative 4.6 times the first vector from C plus 5.8 times the second vector from C. And again, you can double check this, negative 4.6 plus, 11.6 would be 7. And the second one would be negative 1. It works out. All right. And so this matrix here, this 2 by 2 matrix, the left side should be an identity matrix, right? It's a 2 by 2 identity matrix. The right side, okay, the right side, this is that matrix representation of T relative to bases B and C that we're looking for. Okay? So let's see how this is used. What does this do for us? All right. So I'll write that here. So the matrix representation of T relative to bases B and C, right, where B and C were these sets, and B and C were these sets, is this matrix. So we got that it was negative 2.2, negative 4.6, positive 2.6, and 5.8. Right. So again, how is this used? How does this help me? What does this do for me with this transformation? Right. So what this does for me, it does this. If I want the coordinates, all right, if I want the coordinates of some output relative to basis C, right? So if I plug something in, right? If I plug some value, some input into this transformation, get the output. If I want the coordinates of that output relative to C, I can take this matrix and multiply it by the coordinates of the input relative to B. And that'll give me those coordinates. Right. For example. All right, for example. Let's say I were to take T of, I'll just go a simple one, 1, 1. Right. So again, now there's no subscript here, so this is, these are coordinates relative to the standard basis. Now T of 1, 1 would be the vector 2, 0. Right. Again, these are relative to the standard basis right now. Now suppose we want what are the coordinates? We want the coordinates of 2, 0 relative to C. Right, relative to these basis vectors from set C. Right, so from again this set here with the 1, 4 and the 2, 3. Right. Now you could do this a couple ways. I could use my little transition my matrix representation, or do the following. So I guess you could say we could do this. So let's say this is method 1. I already have this matrix. Okay. I need to find the coordinates of this input relative to B. Right, so I take 1, 1, and I'm finding the coordinates relative to B. Now B had vectors 1, 2, and 3, 4 in it. So I put 1, 2 here, 3, 4 here, and then I want to find, what linear combination of these make my input vector 1, 1. All right, now put this into reduced row echelon form. Right. So I'll be back when I have that. Right, so in reduced row echelon form, this is this matrix. Right, so all this is telling me is that 1, 1 is negative half times that first vector from B plus positive half times the second vector from B. And you can double check that. But the way we've been writing this in the past is that the coordinates of 1, 1 relative the coordinates of vector 1, 1 relative to the basis B for the domain is negative half, positive half. Right, so again, all this means is that negative half of the first vector from B plus positive half of the second vector from B will give me the vector 1, 1. Right. So now if I want the coordinates of this output, right, if I want the coordinates of 2, 0 relative to C, I can take my matrix representation and multiply it by these coordinates, the coordinates of my input relative to B. So the coordinates of this 2, 0, right, the coordinates of the output relative to C will be equal to my matrix representation, that negative 2.2 times negative 4.6, 2.6, 5.8, multiplied by these coordinates of the input relative to B, the negative half and positive half here. Right, now a 2 by 2 times a 2 by 1 will be a 2 by 1. All right, and we get positive 1. That's 1.1 minus 2.3. That'd be negative 1.2 for the first coordinate, and then negative 1.3 plus 2.9 be 1.6, positive 1.6, right? Yeah, negative 1.3 plus 2.9. Yeah, positive 1.6 for the second coordinate. And let's see that that works. Let's check. Take 2, 0 and see, is it negative 1.2 times the first vector from C? And again, the first vector from C was, I already forgot here. The first vector from C was the vector 1, 4, and then plus 1.6 times the second vector from C, 2, 3, and let's see if this is working out. So let's see, negative 1.2 plus 3.2 would be 2, and this is negative 2.8. I'm sorry, negative 4.8 plus 4.8 would be 0. This works. All right. So that's all this is saying. That's all this theorem here is saying. Right, back here where it says, again, if you plug a value, you plug a vector into T, and then you would like to find the coordinates of that vector relative to the basis for the codomain C, you can take this matrix representation you found and multiply it by the coordinates of the vector of the input vector relative to the domain basis B. All right, that's what I just did. Now, of course, you can always do it the other way. All right, there is one way to find the coordinates. Now, again, if you want to find the coordinates of 2, 0 relative to C, let's call this method 2. And you can just do what I did to find the coordinates of 1, 1 relative to b. I want to know what linear combination of the c vectors make 2, 0. So remember, those c vectors are 1, 4, and 2, 3. So I put the c vectors on one side, and I want to make find what linear combination of these two make 2, 0. And we put this into reduced row echelon form, and again, I'll come back when that's back, when I had that on my calculator. All right, and do you see those there? The 1, 0, 0, 1, and then you see negative 1.2 and 1.6 that I got. Remember, these were the coordinates I got earlier. All right. These were exactly what I got earlier when I multiplied my matrix the matrix representation relative to b and c, multiplied those by the coordinates of the input relative to b, I got the coordinates of the output relative to c. Negative 1.2, 1.6. So a much quicker way, of course, this second way. But here we're just kind of trying to tie them together with a matrix. Right, we're trying to tie them together, the transition back and forth between coordinates in b to coordinates relative to c. We're trying to tie them together with this matrix representation. All right, so again, pretty hairy, I know. All right, pretty hairy, especially with this first example. I'll do plenty other examples. This is going to be probably a pretty long video. All right, so back to the website. All right, let's look at another example. So again, the first one, they got the now they didn't write them as decimals, but I wrote them as decimals. This is the negative 2.2, negative 4.6, 2.6, and 5.8. All right. Well, let's take a look at example B. Okay, so here's example B. Now this is a linear transformation between some non-Euclidean spaces, right? This is from the set of polynomials of degree 2 or less to the set of polynomials of degree 1 or less. And here's the rule here. My input, a polynomial of degree 2 or less. My output, a polynomial of degree 1 or less. Now, again, I'm going to start off with what we're used to, right? The standard bases. So remember, I'm going to call this E1. Right, now remember the standard basis for P2, every polynomial of degree 2 or less was a multiple of 1 plus a multiple of x plus a multiple of x squared. Right. The standard basis for, let's put standard. That's the standard basis for P2. And then for P1, the codomain, I'll call this E2, right, for the standard basis for the codomain. Remember the standard basis for P1, every polynomial of degree 1 or less is a multiple of 1 plus a multiple of x. So what I can do to find this, I can find the standard matrix real easily by changing everything to coordinates, right? If I change everything to their coordinates, relative to the standard bases, I'd get the following. I'd have T of, and then the coordinates of a0 plus a1x plus a2x squared, well, that's a0 times 1, so a0 would be the first coordinate, plus a1 times x, right? So a1 would be the second coordinate, and a2 times x squared, a2 would be the third coordinate. And again, this is relative to E1 here. These are the coordinates of that polynomial relative to E1. And this will be equal to, and then the output, again, I'm going to write the output as a coordinate vector, right, with the coordinates relative to E2, the coordinates, the basis for the codomain. Well, this is a0 plus a1 plus a2 times 1, right, the constant term, so a0 plus a1 plus a2, that'll be the first component, the first coordinate. I think this is relative to E2. And then plus a1 minus 2a2 times x. So a1 minus 2a2 is the second coordinate. All right, and then from here we can get the standard matrix very easily. Now just write this as a 2 by 3 matrix, where down the first column, the coefficients of a0, 1 and 0, then coefficients of a1, 1, 1, coefficients of a2, 1, negative 2. times our input vector a0, a1, a2, and again these are coordinates relative to e1 here. And here was our standard matrix. Right. Again, I'm hoping this looks familiar, right? This is something you're more used to, working with the standard bases. All right. And this is our, the matrix representation relative to B and C, but B and C are both the standard bases here. Okay. And you can see that the output, the coordinates relative to E2, the codomain basis, is equal to my matrix multiplied by the coordinates relative to E1, the domain basis. And that's exactly what happened, with the last example. All right, so now, we're not working with the standard basis anymore. We're going to change it up a bit. Instead of the standard bases, we're going to have B be the basis for P2. We have 1 plus x squared, 1 plus x, and 1. Right, there. This is a basis for P2, a non-standard basis for the domain. And we're going to have C be the set of vectors 1 minus x and x. And this is a non-standard basis for P1. Again, what I'm asked to find is this matrix representation of T relative to these two bases. All right, so first I just plug in the basis vectors for the domain. So what is T of 1 plus x squared? Well, if I have 1 plus x squared, that means a0 is 1, a1 is 0, and a2 is 1. So I have 1 plus 0 plus 1, that's 2, plus, and then 0 minus 2 times 1, plus negative 2x, or just 2 minus 2x. All right. Then T of 1 plus x, the next basis vector from B. All right, now 1 plus x, a0 would be 1, a1 would be 1, a2 would be 0. So 1 plus 1 plus 0, that's 2 again for the constant term. Then plus x. Right. And a1 was 1, a2 was 0. And then what's T of the third basis vector from the domain, T of 1? Well, 1, that means a0 is 1, and a1 and a2 are both 0. So this would be 1, and then a1 and a2 are both 0, so just T of 1 is 1. Right. So I've got, the first image of the basis vectors of B are, is 2 minus x, the second image is 2 plus x, the third image is 1. So next I'm going to find the coordinates, and what I'm going to do is kind of change these right now to coordinates relative to the standard basis. Relative to the standard basis. This would be, E2. Now this is 2 times 1 and negative 2 times x. So this is going to be the first column on the right side of my adjoint, my augmented matrix. And when I change this to coordinates, this would be 2 then 1. Right, 2 times 1, 1 times x, and then this would be 1 then 0. 1 times 1, 0 times x. Alright, so I'm going to keep these in mind. And now I would like to find the coordinates of these relative to C. Right, relative to C. So I'm going to put the vectors of C over here. Right. So over here, Now, C is 1 minus x. I'm not going to put 1, I can't put 1 minus x. So what I have to do is I have to put coordinates of C relative to the standard basis. So 1 minus x is 1 times 1, negative 1 times x. Right? So down the first column, that represents 1 minus x. X is 0 times 1 plus 1 times x. So this represents 1 minus x. This represents 0 plus x, right? Or just x. And then I have, my images, 2 minus 2x over here, 2 plus 1x over here, and then, 1 plus 0x. Right? And over here are the coordinates of the images relative to the standard basis. Right? Coordinates of the images relative to E2. Right? And then I put this into reduced echelon form, which would be very, very simple. I don't have to go to a calculator for this. All I would need to do is add row 1 to row 2. Get a new row 2. So I got 1, 0. So the first row is not changing. And when I add these, 1 plus negative 1 is 0, 0 plus 1 is 1, 2 plus negative 2 is 0, 2 plus 1 is 3, 1 plus 0 is 1. And here are the coordinates. Right? And then this would be my matrix. Right? This right here, this 2 by 3. This is the matrix representation of T relative to basis B and basis C. And let me show you that these actually work here. These are the coordinates of this relative to C. So do you see that 2 minus 2x is equal to 2 times 1 minus x plus 0 times x, right? Which is clearly true. Then this column here, 2 plus x, right? 2 plus x is 2 times 1 minus x plus 3 times x. Right? 2 times 1 minus x plus 3 times x. And that's clearly true. And then 1 is 1 times 1 minus x plus 1 times x. Right? 1 times 1 minus x plus 1 times x gives me 1. So these perfectly represent the coordinates of those images relative to C. All right, so check on all those. All right, so I'll write that on the next page and then show you again an example of how to use it. All right, how would we use this? So the matrix representation of T relative to B and C here is this matrix, 2, 0, 2, 3, 1, 1. Right. Right, and then again, how this would be used. The coordinates of some output. So say T of x. If I were to plug some polynomial into this transformation, and then I said I want the coordinates relative to C, I can take this matrix and multiply it by the coordinates of the input relative to the domain. Right. And let's see this in action. Right, let's actually see this in action. Right. So again, here's the transformation. And let me just do, for example, say I want T of, my input's just some polynomial, relative to some polynomial degree 2 or less. How about T of 1 plus 2x plus 3x squared? Right. So let's see, that would be equal to 6. All right, 1 plus 2 plus 3. And then 2 minus 6, so minus 4x. Right. Now these are, just plugging into the normal rule. Now what I'm saying is now we would like the coordinates of this 6 minus 4x relative to C, relative to basis C. Okay. All right. So again, there's a couple ways to do this. One is change the coordinate. Let's find the coordinates of the input relative to B and multiply it by our matrix representation. Find the coordinates of 1 plus 2x plus 3x squared relative to B. All right, so again, the easy way to do that is with a matrix. Now B was this set here. So I make a little augmented matrix right now. Down the first column I got 1 and then 0x and then 1x squared, and then down the second column 1, then 1x, then 0, and then 1, then 0x, then 0x squared. And then I'd like to know what linear combination of these three make my 1 plus 2x plus 3x squared. So make 1, 2, 3. And I'll put this into reduced row echelon form. Right. So I'll be back when I have that. Okay, so we're getting this. All right, and again, all this is telling me is that 1 plus 2x plus 3x squared is equal to 3 times 1 plus x squared plus 2 times 1 plus x plus negative 4 times 1. Right? And you can double check this. This is true. Right? This is working out. Okay, so here are the coordinates. Right? So the coordinates of 1 plus 2x plus 3x squared relative to basis B is this vector here, 3, 2, negative 4. And I'm going to multiply this by our matrix representation, right, by this guy here. And that'll give me the coordinates of the output, right? So the coordinates of the output, right, the output was 6 minus 4x. The coordinates of 6 minus 4x relative to C, I could find now this way, by taking my matrix representation, 2, 0, 2, 3, 1, 1, and multiplying it by the coordinates of the input relative to B, right, which I have here, 3, 2, negative 4. And this is a 2 by 3 times a 3 by 1, so this is going to be a 2 by 1. And I'll have what? 6 plus 4 is 10, minus 4 is 6, and then nothing, 6 minus 4 is 2. All right. And there we go. All right. And let's check. Take the vectors from C, right, which were 1 minus x and x, and see if this works out. Is 6 minus 4x equal to 6 times 1 minus x plus 2 times x? Is that true? Absolutely. So here are the coordinates, and again, it was found the coordinates of my output relative to the basis for the codomain. Take that matrix representation, multiply it by the coordinates of the input relative to the basis of the domain. Now I could have also done this, right? If I wanted the coordinates of the output relative to C, remember the output was 6 minus 4x. If I wanted the coordinates of those relative to C, I could have done this, put the vectors of C, their coordinates relative to the standard basis. You got 1 and then minus 1x and then 0 times 1 plus 1x. Put the, this represents 1 minus x, this represents x, and then put, 6 minus 4, 6 minus 4x. And then just put this in reduced row echelon form, which is really easy to do here. You just add the rows. You'd have 1, 0, 6, and then 0, 1, 2. And you see 6 and 2 there. Right? The same thing I got earlier. Much faster, of course, but that's not the point of this section. The point of this section is to find this transition. Right? Find this transition from, this relationship between bases B and bases C. Right? And that's this matrix representation relative to those two bases. So again, finding the matrix usually won't take that long. I'm not going to be doing an example every time, but so you can see they found it here. All right. So again, here, find the matrix representation for the linear transformation. This time from P2 to P3, defined this way, with respect to basis B and basis C. Right. So B is a basis again of the domain, C is a basis of the codomain. And then they do the same crap where plug in 1, plug in 1 minus x, plug in x minus x squared, and then find that matrix representation. So I can do that. I'll do that really quick this time. This shouldn't take too long to find this matrix representation relative to two different bases. Alright, so here it is again. You have a basis for the domain, basis for the codomain that are not standard. And you still have to use the standard matrices, the standard bases, for some coordinates. Because of my, well, let's get into it. All right. So first, I find what's t of 1. Well, it'd just be 1 minus x times 1. Right? So just 1 minus x. Now again, what I'm going to do when I write the columns of a matrix, in my augmented matrix, I'm going to be putting it into reduced row echelon form in a second. Over here, I'm going to write the coordinates relative to the standard basis for P3. Which would be this, 1x, x, and x squared, right? I'm sorry, 1x, x squared, and x cubed. Sorry, that's 1x, x squared, and x cubed. There's the standard basis for P3, right? Polynomials of degree 3 or less. So 1 minus x would be, 1 times 1, negative 1 times x, 0 times x squared, 0 times x cubed. So this will be a column I write in my augmented matrix. All right, then t of the next basis vector from the domain, 1 minus x. Well, that would just be 1 minus x times 1 minus x again. So that'd be 1 minus 2x plus x squared. Now again, if I change this to coordinates relative to the standard basis for P3, it's 1, negative 2, 1, 0. And then finally, the third basis vector from B, t of x minus x squared. Again, that's just the way the rule looks. That's 1 minus x times x minus x squared. Well, this would be x, and then minus x squared minus another x squared, so minus 2x squared, and then plus x cubed. All right, changing the coordinates relative to the basis, the standard basis. You'd have 0, 1x, negative 2x squared, 1x cubed, like this. All right. So now, I want to find what are the coordinates of these vectors here. What are the coordinates of these vectors relative to basis C? And again, I'm going to write the basis C vectors relative to the standard basis. I'm going to write them as coordinates. Everything is coordinates. So I'm setting up this matrix. So on the left side, I'm going to put the basis C vectors. Now this one is just 1, 0x, 0x squared, 0x cubed. 1 plus x is 1, 1x, 0x squared, 0x cubed. 1 minus x squared is 1, 0x, negative 1x squared, 0x cubed. And then x plus x cubed is 0, 1x, 0x squared, 1x cubed. Right, so here are the vectors from C. Right, here are the basis C vectors, written in terms of coordinates relative to the standard basis. And then over on the other side, the three vectors I want to find the coordinates of relative to C. So the 1, negative 1, 0, 0, 1, negative 2, 1, 0, 0, 1, negative 2, 1. And then I put this into reduced row echelon form, which again, I'll go to a calculator and enter this, what is this, a 4 by 7 matrix. And I'll pull that up when I'm done. Right. So put that all in reduced row echelon form. Again, on the left side here, I got the 4 by 4 identity matrix. And on the right side is that matrix representation of T relative to bases B and C. So 2, 4, negative 2, negative 1, negative 2, 0, 0, negative 1, 2, and 0, 1. And again, remember what this means. All right. This means that 1 minus x, all right, 1 minus x represented by this column is, and this is relative to basis C, is 2 times 1 minus 1 times the 1 plus x, right? This is relative to basis C, and then plus 0 times 1 minus x squared plus 0 times x plus x cubed. And yeah, this works. Then the second column means that 1 minus 2x plus x squared is 4 times 1 minus 2 times 1 plus x minus 1 times 1 minus x squared, and then plus nothing. And again, check that. And this works out too. And then this last column means that x minus 2x squared plus x cubed is negative 2 times 1 plus 0 times 1 plus x plus 2 times 1 minus x squared plus 1 times x plus x cubed. And that also works. Alright, so there it is. There's our matrix representation of T relative to these two bases. This 4 by 3. Now be careful. I wrote my standard bases in this order with the constant first, right, and then x cubed last. If they write it in the other order, all that would change is these would reverse, right? So sometimes the order matters, right? These are ordered bases. So just pay attention. Yeah, so looking like that one, right? So they kept the same standard basis that I had. Right? All right, and that's what you're asked to do for the challenge activity. All right. And this first one, you're given a transformation from R2 to R2. They're saying let U equal 8, 9, the vector 8, 9. And C basis C is 1, 0, negative 2, 1. So it says find T of U. All right, so what would just plug it in like normal. What's T of U? And then what would the coordinates of this be relative to this basis? All right, so you don't have to find any matrix representations here. So that should be simple enough. Let's take a look at what the other levels look like. All right, this one they're actually asking for the augmented matrix you would set up before you put it in reduced row echelon form. So again, you got the vectors of C on the left and then those images of the vectors of B on the right. That's all you're asked for there. And this is now actually find that matrix representation relative to the two bases given. And this is also the same thing. But like again, this is pretty similar to the last example I showed you where you're dealing with polynomials. Just remember to convert everything to coordinates, right? Because you're not going to be able to put polynomials in your matrices here. Okay, and then find that matrix representation. All right. So now the final part of this, and it's been pretty long. It's gonna, this is pretty heavy here. Change of basis and the matrix representation of a linear transformation. All right. So when a change of basis occurs, the matrix representation of the linear transformation also changes, right? Because if basis B and basis C all of a sudden become different bases, well then this would be a totally different matrix. The effect of a change of basis on the matrix representation of the same linear transformation is summarized using the theorem below. So suppose T is a transformation from U to V, and it's a linear transformation. Say B is a basis for the domain, and C is a basis for the codomain, and this is the matrix representation with respect to bases B and C, right? The notation you've been seeing. Then, for every vector in the domain, PC times T of U is equal to the matrix representation times PB, this is technically times U here, where PB is the transition matrix from the standard basis of U to B, and PC is the transition matrix from the standard basis of V to C. All right, that's a lot, but I like this picture here, and I'll draw this up actually on some paper and explain what's going on. All right. So if we look at any linear transformation and called T. So again, here's set U, the domain. Here's set V, the codomain. And if we're looking at vectors from U with their coordinates, I'll call this like a coordinate map here. Coordinate map, because everything I mention is going to be in when I mention standard basis or some other basis. I mean, I want to write all my stuff as coordinates relative to that basis. So I'm going to say it's a standard basis, E1, and over here we'll look at vectors in V in terms of their coordinates relative to the standard basis for V. And let's call that E2. All right. So if I take a vector, so again, here's a set U, here's a set V, and right now it's everything's in terms of the standard basis. So if I take a vector from U called U, and again this vector is written in coordinates relative to the standard basis. Now I can just straight up plug it into T. Alright, plug it into T, and that would give me, T of U. Now another way to say this is I could also take U and multiply by the standard matrix for T, which in previous sections usually was just called A. So this T of U could be represented by A times U. Right. And I'll be given, when I multiply those, I'll get coordinates of the output relative to the standard basis E2, the standard basis for V. Now, if I wanted to, I could take the coordinates of u and write them in terms of the coordinates for a basis B. So again, we still have set u here, domain vectors. But now I'm going to take u and change it to the coordinates of u relative to basis B. And in order to do that, you're going to be multiplying by this matrix here called P sub B. All right, this is going to be the transition matrix. Maybe you remember this notation a little better. I would go from E1 to B. All right, you remember this notation with the arrow underneath the matrix? This is I'm translating coordinates from coordinates relative to the standard basis into coordinates relative to basis B. All right, and then once I'm in basis B, if I want to talk about going to writing coordinates of the output in basis C, and this is vectors in V, the output, the codomain set, I could do two things. I can get there in two directions. One is, again, I plug in U, and then I can take this output in terms of the standard basis of V, and change it to its coordinates relative to basis C, relative to this new basis for the codomain C. And to do that, to change from standard basis to coordinates in basis C, I'm going to be multiplying by this PC, which again would, in older notation, would be going from E2 to C. Remember to find that transition matrix. Now I could get there another way as well. Remember we said this earlier. So I start off in standard basis coordinates, I change it to base B coordinates, and then I multiply by that matrix representation relative to B and C. Then I multiply by T relative to B and C here. And that gives me T relative to B and C. My matrix representation gets multiplied by the coordinates of the input relative to B. And you saw this earlier. This was written earlier. The coordinates of the output relative to C are equal to this matrix times the coordinates of the input relative to B. All right. But we can, applying these other matrices, see all sorts of different relationships. I could say that this is also equal to PC times T of U. All right, because I took T of U and multiplied it by this PC. Or, remember the coordinates of U relative to B here are just PB times U. All right, this is equal to PB times U. Taking U, multiplying by PB, then taking the coordinates of U relative to B, multiplying it by the matrix representation, or taking U, multiplying it by the standard matrix A, and then multiplying by PC. Right, so we're getting a lot of stuff here from this coordinate map. So what we're seeing in the end is that PC times T of U, so times A times U. Right, again, A is the standard matrix, PC is the transition matrix from the standard basis of V to C. This should be equal to our transition matrix, our matrix representation multiplied by PB multiplied by U. Right. And so what we're seeing here is that if I subtract things from both sides and factor out the U, PC times A minus our matrix representation times PB, this would be equal to the 0 vector. Right. And as long as this matrix here has a a non-trivial null space, if the null space is only trivial, the only way this is going to be 0 is if u is 0, or if this is 0, and we can say then that PC times A must be equal to our matrix representation times PB, and therefore our matrix representation must be equal to PC times A times PB inverse, multiplied by the inverse on both sides. This is something we're getting out of this as well. There's a lot of stuff coming from this, all right, but I like to just think of this map. And this is what all this stuff here that they're saying is coming from this map, and I've drawn the map a little more detailed. All right, so I know that's a lot of notation. That's a lot of notation. So let me show you an example. All right, let's do this example here. Okay, so this is that same example from earlier. T from R2 to R2 is described this way. We're looking at, this is basis B for the domain. This is a new basis C for the codomain. And you have the standard bases, 1, 0, 0, 1. All right, so I'm going to write this in terms of the standard matrix. And this would be coefficients of x1, coefficients of x2 times x1, x2 like this, right? So this is that A, right, the standard matrix A. And then what I want to find is that PB and PC. So to find PB, right, again, this is the transition matrix from the standard basis to basis B. I make an augmented matrix here where I put the vectors of B down these columns, and then the standard basis vectors over here, right, 1, 0, 0, 1, and then put this into reduced row echelon form. Okay. Now really, since this is the identity matrix here, really all I'm finding is the inverse of this, so this won't be so bad. I'm going to say this PB then is just going to be the inverse of 1, 2, 3, 4. So what is that? 4 minus 6 is negative 2, negative 1/2 times the vector, the matrix 4, 1, negative 3, negative 2, like that. Right, there's PB. All right. Because remember, this is how you find inverses of a matrix too, right? Where you have the identity over here. And the same thing would go for PC. Right, same thing would go for PC. Transitioning from the standard basis for C for R2 to the vectors from C, right? For the to the coordinates of basis C. So I put the basis C vectors here, 1, 4, 2, 3, and the standard basis vectors here. And if I want to put it in reduced echelon form, I could, but again, this is only a 2 by 2 matrix. So we can see that PC is going to be what? This is 3 minus 8, so negative 5. So you got negative 1/5 times the matrix 3, 1, negative 2, negative 4. Okay, so there's the matrix PC. And then using these, right, remember I can find that matrix representation. I just wrote up on this paper here that the matrix representation of T relative to B and C is, PC times A times PB inverse. And PB inverse would just be what I started with before I found PB. Right? PB inverse is just simply the matrix where vectors from B are the columns. Same thing would be for PC inverse. PC inverse would be a matrix where the columns are just from C. Right. And like I said, what I'm going to do is I'm going to draw up a map. Right. I'm going to draw up another map, a coordinate map, like I did before. All right. So here we have R2, but relative to the standard basis, say E1, right? Basis, E1 basis. And then over here I have R2 again with the codomain, say relative to E2, again the standard basis. So if I take a vector, x1, x2, I plug it into T. I plug it into T, which means just multiply by A. Right, multiply by A, multiply by the standard matrix. We would get T of x1, x2, or just A times x1, x2 as a result. And then on the bottom of this map, got R2 again over here, the domain, but this time relative to basis B. So one thing I could do is I could change the coordinates of my input to the coordinates relative to basis B, right? The coordinates of x1, x2 relative to basis B, and in order to do that I would just multiply by that PB, right? That transition matrix. So this would be PB times x1, x2. And then over here in the lower right corner of the map, I have my codomain again, R2, but relative to basis C. And I can get there in two different directions now, right? I could take my output up here and just change it from the standard basis coordinates to basis C coordinates by multiplying by PC. So I'd have PC times A times x1, x2. Right? That's giving me the coordinates of T of x1, x2 relative to C. Sorry about the clutter there. Right. But it's giving me the coordinates of the output relative to C. Or I could get there coming from this direction, multiplying by our transition matrix, not our transition matrix, but our matrix representation relative to B and C. So this is equal to the matrix representation relative to B and C times PB times x1, x2. Right. So again, you see how these got to be equal, PC times A and our matrix representation times PB. So then this statement would be true, right? These got to be equal. So then our matrix representation has to be equal to PC times A times PB inverse. Let's see what happens when we do that with this example. Do PC, let's do PC times A times PB inverse. Well, that would be this negative 1/5 times 3, negative 2, negative 4, 1. Right, there's PC. A was the standard matrix, right, from the way it originally looked, the 1, 1, 1, negative 1. And then again, PB inverse is just the matrix where the vectors from B are the columns. So 1, 2, 3, 4. And if I multiply these, negative 1/5 times, let's do these two first. What is that? 3 minus 2 is 1. 3 plus 2 is 5. Negative 4 plus 1, negative 3. Negative 4 minus 1, negative 5. And then times 1, 2, 3, 4. Negative 1/5 times, and then 1 plus 10 is 11. 3 plus 20 is 23. Negative 3 minus 10, negative 13. And then negative 9 minus 20, negative 29. Alright, and if I put in negative 1/5 in there, you see that'd be negative 2.2. All right, 11 over 5, and then 23 over 5 would be negative 4.6, if I'm writing decimal. 13 fifths would be 2.6, and then 29 fifths is 5.8. That look familiar? I mean, I know it's been like probably an hour, but this was what I got way earlier. I lost that paper. Anyway, this is what I got earlier for that matrix representation of t relative to that basis b and c, because this is the same example we saw earlier. Okay, but that's neither here nor there. What are they asking us to do here? They're asking us to, one, find p of c times t of u, where u is the vector negative 2, negative 4, and then find the matrix representation times p times u, and what you're going to see is that these are the same, right? Again, what I've written here, pc times a times the vector is t of the vector, right? That will be equal to the matrix representation times pb times the vector. That's what they're saying. They should be equal. So for parts A and B, you should get the same result. So going back here, we have PB, we have PC, we have our matrix representation. So the first thing they want is, if u is the vector, 2, negative 4. Let's find, PC times t of u. All right. So t of u. Now PC I know, right? That'd be I found that earlier. That's just negative 1/5 times the matrix 3, negative 2, negative 4, 1. Right? I found that earlier. And then again, t of u is going to be the standard matrix times, and then u here is the vector 2, negative 4. All right, let's see what we get here. Multiplying these two. I think I already did that. Right? Yeah, I did that here. It was 1, 5, negative 3, negative 5. And then times, 2, negative 4. Yeah, 2 minus 20, negative 18. And then negative 6 plus 20, positive 14. And we're getting this here, positive 18 fifths, and then negative 14 fifths. Okay. And according to that theorem, this should be the same as what I would get if I took the matrix representation and multiplied it by PB, and then multiplied it by the vector 2, negative 4. I should get the same exact result. All right. Again, you're seeing that here. I'll let you read that out. See, they're getting the 18 fifths, negative 14 fifths. And you see they're getting the exact same result when I take that matrix representation, multiply it by PB, and then multiply it by the vector. Right. So then finally they're saying, oh, well, if that's the case then, if these two are equal, right, if these two are equal, well, then I should be able to find the output. And I'll write this on paper. So from this matrix theorem, representation theorem, since these are equal, right, since the matrix representation times PB times my input vector, since this is equal to PC times t of u, and this is for any u, then T of U should be equal to PC inverse times my matrix representation, or multiplying by PC inverse on the left, and then multiply by PB, and then multiply by the input vector. Right? So like I said, this is just the standard matrix. So the standard matrix can be found this way as well. It's weird, right? A lot of stuff. So let's play with this. And I think they have us doing that in the next example. Right. So, and yeah, you got a challenge, and that's it. Okay. So the next example, now here we're given a linear transformation between, this is the same one as earlier. Right, it's the same one as earlier. So I'm going to find all those matrices. I'm going to find now we found the TBC here. We found that matrix representation earlier. So I'll pull that back up. This is the same example as earlier with the polynomials. And then we're going to fill in these blanks. All right. Okay, so we saw this same example earlier. So we found earlier this matrix, right? The matrix representation relative to these two bases was, wrote it down here, it's this matrix here, 2, 0, 2, 3, 1, 1. Alright, so now what I wanted to do is find PB, PC. Right? So for PB, I'm setting up an augmented matrix where I'd like to, I'm transitioning from the standard basis to basis B. Now the basis B vectors, when you write those relative to the standard basis with 1x and x squared, that'd be, 1 plus x squared is 1, 0, 1. Right? 1 plus x would be 1, 1, 0, and then 1 would be 1, 0, 0. Okay, and then you have representing the standard basis 1, 1 x, which would be 0, 1, 0, and x squared would be 0, 0, 1. And then I'd find, put this in reduced row echelon form, or just find the inverse of this matrix, because that's really what you're doing. All right, and then the inverse, this is PB, this would be called PB inverse, right? And PB would be the inverse of this. Now I can do reduced row echelon form, or just write the inverse of this, which I'll pull up on my calculator. Alright, so finding the inverse of this 3 by 3, we see that PB is the matrix 0, 0, 1, 0, 1, 0, 1, negative 1, negative 1. Okay, there's PB. I'd also like PC. So PC, well, as I mentioned before, PC inverse is just the matrix where, these guys are the columns, but again, written in coordinates relative to the standard basis for P1. So 1 minus x would be 1, negative 1. X would be 0, 1. All right. And this one's a pretty easy one to find the inverse of. PC then, the determinant is 1. So the inverse is just 1, 0, 1, 1, like that. Right, there's PC. Okay, so I have really all the matrices I need. And again, I'm going to draw that mapping again. I'm going to draw the coordinate map. Talk about what's happening. So up top we got P2 in the domain. Now this is relative to the standard basis, E1. Right, 1x and x squared. Then over here we have P1, the codomain, relative to the standard basis, 1 and x. That'd be E2. And again, if I start with some polynomial, now again, this is the polynomial. This is a polynomial written in coordinates. All right. So I'm going to write the polynomial in terms of coordinates relative to the standard basis. And plugging that into t, is again really multiplying by A, right? The standard matrix. I would get T of U, which is the same thing as A times U. Again, this is all in coordinates though. All right, my output will be the coordinates relative to the standard basis. And then down the bottom you have P2 at the domain, but relative to basis B. And then over here P1, the codomain, relative to basis C. And if I want to get down here, one direction I could take is, I change U, take the coordinates relative to the standard basis, multiply by PB, and I get PB times U, which are the coordinates, relative to basis B. And then I multiply these by our matrix representation relative to B and C, and it takes me here, which gives me the matrix representation relative to B and C times PB times U. And that should be equivalent to if I took this here and just multiplied it by PC on the left. It should be equivalent to PC times T of U. Again, this T of U is coordinates relative to the standard basis for P1. All right. Yeah. So the first part of this problem, they're asking us to find this. What's this times this times this matrix representation times PB times U, where U is this polynomial. Right. So U, they're telling us U is 5 plus 3x minus 4x squared. But again, every time on my map here, every time I see something, it's in coordinates. So U should be in coordinates relative to the standard basis, which would be 5, 3, negative 4. Okay, so that's going to be my U here. So then the matrix representation times PB times U would be this. Our matrix representation was this 2 by 3, 2, 0, 2, 3, 1, 1. That was earlier. PB I found. PB was this 3 by 3 matrix here. 0, 0, 1, 0, 1, 0, 1, negative 1, negative 1. And then times U was this 5, 3, negative 4. All right. Okay, so 2 by 3 times a 3 by 3 is going to be another 2 by 3. So multiplying these two gives me what? You got 0, 0, 1, 0, 2, minus 1 is 1, 2, minus 1 is 1, and then 0, 0, 1, 0, 3, minus 1 is 2, and 0, 0, negative 1. And then times the 5, 3, negative 4. And finally we get down to this, right? A 2 by 3 times a 3 by 1 will be a 2 by 1. 5 plus 3 is 8, minus 4 is 4. And then 5 plus 6 is 11, plus 4 is 15. And what this should give me, all right, according to my map, this T, right, this T times PB times U should give me the coordinates, right, these should be equal to the coordinates of T of U relative to the basis C. Right. Now on the website, just putting 4, they're just having me fill in the coordinates 4 and 15. This is kind of I'm gonna send some feedback about this, because really it should be 4 times the first vector from C, 4 times 1 minus x. Ooh, yeah, you know what? Maybe that's what they want us to do. All right, so let's go back here. Remember, remember this result, this T times PB times U gives me the coordinates relative to C. So back in the normal part, that'd be 4 times 1 minus x plus 15 times x, right? These are the vectors from C. And when I multiply this out, this would be 4, and then minus 4x plus 15x be plus 11x. So they want me to fill in the 4 plus 11x here. Right, so putting in 11. Yeah, I know. That should be 11. It shouldn't be 15. No, that's not right. Should be the should be the coordinates. So just put the coordinates here relative to C. Looks like 4 and 15 are what they want. But they should have written this out as 4 times 1 minus x plus 15 times x, not like this. Okay, so put the coordinates here, but they should have written that out another way. I'm gonna send them some feedback about that. All right, so then we're asked to find what's this previous result. See, this is the previous result times PC inverse. Remember, PC inverse is just a matrix where those columns are from the vectors from C. Right. Back here, again, looking at my map, if I multiply this result by PC inverse, I'd just be getting what T of U is. Right. So take this previous result. Now T of U should be, again, PC inverse times this 415. Now PC inverse, right, I already wrote that. Right, PC inverse was, again, just this 1 minus x and x with the, written in terms of coordinates. So 1, negative 1, 0, 1 times the 415 here. And a 2 by 2 times a 2 by 1 is a 2 by 1, you get 4. And then 11, this is where the 11 should come in. All right. And this T of U, right, this is back on the map. T of U belongs up here. So these should be coordinates in terms of the standard basis, 1 and x. So this is 4 times 1 plus 11 times x. All right. Okay. So back here, this should be just T of U, 4 plus 11. All right. Great. Yeah. So again, the way they had this written, I don't like, because it should have been 4 times the first vector from C plus 15 times the second vector from C. But just enter the coordinates here, and same thing here. The coordinates at the end here, this PC inverse, this should be T of U, and T of U is back in the standard basis for the codomain. Right, so I want to write the output in terms of the standard basis 4 plus 11x. All right, and then the challenge activity. Let's take a look. This is just going back through remembering what relationships were there. This is true, right, from my map. And if this is true, multiplying by PC inverse, this is true. And that would be about it. Okay. All right, and let's take a look at the other levels. All right, so they're asking you to find that transition matrix from, the standard basis of the domain to basis B. So that shouldn't be so bad. Third level is, if you had that matrix representation, which you found, which was found in the first half of this video, how to find that, multiply it by PB, and then multiply it by U, where U is negative 1, 1 here. What's the resulting vector? and those should be coordinates relative to basis C. All right, and the same thing here. What's T of U, and then multiply that by PC. All right, so you have to find PC, which is basically just the inverse of this 3 by 3 matrix. Then find T of U, write it as its coordinates and multiply those. Right? This shouldn't be so bad either. All right, then you have your additional exercises. Again, some of these are assigned, some are not. I would still recommend looking at all of them just to get used to the material, more practice, more exposure. You can also click on these solutions if need be. I hope they're not doing what they did up here, where they had the coordinates in, but they should have had 4 of the first vector from C, 15 of the second vector from C. Hoping they're not doing that too much. And you can always look again. You can look at the solutions. Please don't look at them right away, though. Try to work these out on your own before you do, right? Because if you're just copying solutions and not trying, you're not going to learn anything. And I know this is a lot, right? And this is the end of chapter 7. This is heavy, right? This is heavy on notation, heavy on mappings, and change of bases and all that. Heavy on coordinates. All right, you're dealing with lots of coordinatization now, and it is very easy to get confused. Which basis am I looking at? What coordinates should I be writing? I would recommend drawing those maps, actually, those coordinate maps. Or on the top, you have the transition from standard basis of the domain to standard basis of the codomain. And on the bottom, you got the transition from basis B of the domain to basis C of the codomain, and all the links and all the matrices you'd have to multiply by to get from one position to the next. All right, and obviously if you have any questions, send them my way and I'll get back to you as soon as possible. I'm open this video, and I do have several other videos in Canvas related to these same topics. So I'm hoping where I go over other examples. I'm hoping watching those help you out as well. And I hope you have a relatively easy time understanding this stuff. And thank you very much for watching.